Now you go into a multiplexer. So a multiplexer is that if you have a 2-to-1 multiplexer, it will choose between two inputs. Okay, so if S is equals to 0, the output will follow D0. So S equals to 0, Y equals to D0. So here, if D0 is 0, Y is 0, and if D0 is 1, Y will be 1. And the reverse, if S equals to 1, S equals to 1, Y equals to D1. Okay, so this will follow this. Okay, so nothing special about this. You have already learned multiplexers. So multiplexers can be formed into can be broken down into little gates, right? So if you put in the equation for the marks right over here, so you can see here S equals to D0, Y equals to Z0 plus, okay, sorry. So when you write the equation over here, equals to D0 multiplied by S, but S is bar, plus D1 multiplied by S. You can put this equation here. So how many transistors are needed over here? So you can draw this Y and into the gates. So in this one you will have the AND gate. So this is S and this is D1, and you have another AND gate here, S bar and D0. This is the AND gate and this is Y. Okay, we break them down further. So as you can see here, this one between S and S bar, there should be an inverter. You need an inverter over here, so this will become S bar, right? Okay, so now when we want to transform this, when we want to calculate how many transistors are needed, we need to transform these AND gates into Nand gates and the OR gates into NOR gates. So the AND gate, we know that the Nand gate has 4 transistors, right? So what is the transistors in a Nand gate? It is like this. Okay, this is the Nand gate. So we are going to transform this circuit into a NAND version. You can see over here we are transforming an AND gate into a NAND gate, which consists of a NAND gate and an inverter. So one AND is equivalent to a NAND gate plus an inverter. Okay, similarly an OR gate is equivalent to a NOR gate plus an inverter. Okay, so if you transform this, the NOR gate, you get the OR gate, you get a NOR gate plus an inverter. So the total number of transistors needed is, firstly, this, the first inverter has 2 transistors. This each NAND gate has 4 transistors as we showed before. So 2 plus 8 plus each of these inverter has 2 transistors plus 4 plus another 4 from the OR gate plus another 2, then you get a total of 20 transistors to perform this equation. Okay, so we need to reduce the number of transistors, and how can we do that? We can reduce it by using a transmission gate mux. The transmission gate mux has the circuitry shown here, which consists of 2 transmission gates which are connected back to back. So as you can see here, the first part, so let's draw the first part. I'm going to draw the first section. So this is S and this is D0. Over here is S bar and this is Y. So let's look at what will happen when we put the truth table over here. So you have D0, S and Y. Okay, so let's put 0, 0. Okay, so let's put here D0 equals to 0, S equals to 0, and S bar will be the inverse of S, so it will be equals to 1. Okay, so in this case you can see over here this NMOS transistor, because S bar is 1, it will be turned on, and S equals to 0, it will turn on the PMOS. So D0, Y will follow D0, so since D0 is 0, Y will be 0. Okay, let's look at what will happen in the next instance. So if you have 0, 1, okay, here everything is the same except for S is equals to 1 and S bar will be equals to 0. In this case, the NMOS will turn off and the PMOS will also turn off. So in this case, this part will be open and this also will be open. So Y will be Z. Okay, let's look at the different instance here. When D0 is equals to 1 and S equals to 0. Okay, so here to 0 and S bar will equals to 1, and then the Y will follow the D0. In this case, D0 is 1, so Y will be 1. Okay, and if you put in the next instance, which is 1, 1, because S is 1, S equals to 1, which is here, and S bar will be equals to 0, both will be off, so this will be a Z. So if you write the equation over here, Y will be equals to D0 S bar. Okay, so this transmission gate can perform the equation of Y equals to D0 S bar. Okay, let's look at the second part of the equation. So the second part of the equation is given by the next part of the circuit, which is the next transmission gate. So if we test it over here, this is S bar, and the S bar is connected to the gate of the PMOS, and S is connected to the gate of the NMOS. So this is D1 and this is Y. So if we look at the truth table, D1, S and Y, you start with 0, 0 here. This is 0, this is 0, then this will be 1. All the transistors will be off, the NMOS will be off, the PMOS will be off, and the Y will equals to Z. So if the reverse, if D is 0 and S equals to 1, so now here S equals to 1 and S bar will equal to 0. As you can see, this transistor is now on, the NMOS will be on, and the PMOS will also be on. So Y will follow D1. In this case, D1 is 0, so you get 0. So if you have a different input, so the next part of the truth table, 1, 0, this will obtain a Z because the S is off. And if you continue, 1, 1, the Y will follow the D1 and Y will follow D1. In this case, Y will be equals to 1. So this implements Y equals to D1S. So now we are going to put them together. This is to perform the OR function. So the total y will be y equals to d0s bar plus d1s. So this is the final equation. So as you can see here, instead of having 20 transistors from the previous circuit, we now only need 4 transistors. Okay, very simple using transmission gates. We can also implement an inverting multiplexer using this circuit over here. So let's see how to implement it. So if you can see here, the two series NMOS transistor will implement y equals to Z0S bar, and since it is at the NMOS, you are going to bar the circuit, bar the y. Okay, and this on the right hand side, it is implementing D1S. Okay, D1 multiplied by S. So you will also put the PMOS part, and this PMOS is in parallel. So let us redraw here in series. This is S bar, and this is D0, and this is S and D1. So this implements D0S plus D1S bar, and you can put the complement. So the complement for this side here is actually this branch here. This is D0 and this is S bar, and the complement from over here is actually this side over here, where this is D1 and S. Okay, so this will implement this equation. Okay, other than that, we can also form a 4-to-1 multiplexer using two different methods. The first method is 2 levels of 2-to-1 mux. So this is the first level. You have 2 sets of a mux, and then you have the second level. Okay, the second level implements the S1, and the first level implements the S0. Okay, another method is to use 4 tri-states buffers. So as you can see here, 4 sets of tri-state buffers. You have D0, D1, D2, D3. One set of tri-state buffer for each input. So this one will implement the 4-to-1 multiplexer.